Our second speaker this morning is Mauro Maggioni.
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 Yes.
I always think of Mangioni because of this trumpet player from the 70s, Chuck Mangioni. I don't know. I get that name, and you hear that. Yeah. Okay. Sorry. At any rate, Mauro is arguably the world's leading expert on multi-resolution, multiscale analysis of graphs and networks and things like that. And so it's a real pleasure to have him here. And today he's going to talk about multiscale methods for the analysis of dynamic something.
Oh, I added two words to the title because, the missing word is graphs, of course. But I added two words because this is a work in progress, and my main collaborator here is Jason Lee. He's one of our undergrads at Duke, and he just graduated and is off to Stanford for grad school. It's a pleasure to be here today, and thank you very much to the organizers for having me here. I think I'm the second outlier in two speakers this morning because I've just started recently working on networks, and the type of graphs and networks that I work on are a little bit different than communication networks and internet networks. In fact, quite a bit different sometimes. And so I wanted to tell you a little bit about the graphs and networks that I'm used to work on, and then move from there. And I divided the talk into three sections. One a little bit about graphs coming from high-dimensional data sets. A second part where I try to do multiscale analysis on those graphs. And then a third part where I apply that to the case where graphs change in time. And I hope to get to all three parts. So how do graphs arise from high-dimensional data, and which kind of high-dimensional data are we talking about anyway? So here I have two examples. The first example is a set of documents. It's a set of 1,000 scientific articles taken from Science News. And how do you map them to high-dimensional vectors? Well, you can pick a dictionary. Here I picked a small selected dictionary of about 1,000 words. And the kth coordinate of any document is simply how many times the kth word in the dictionary appears in that document. And if you do that, you get the matrix whose rows are indexed by documents and columns are indexed by words, and the ij entries is how many times the jth word appears in the ith document. And you can ask lots of questions. These documents, it's like a point cloud in 1,000 dimensions. You can ask, is there any structure there? If you look at the matrix, you shouldn't see anything. But still is there useful information in there? Can you visualize this data? Can you do any sort of learning? Can you discover that there are different topics in these documents, and so on? And you can ask similar questions of many other data sets. Here is a data set of images of handwritten digits. You could ask for an algorithm that automatically recognizes digits, and so on. Here you have about this standard data set. It would be, say, in the tens of thousands of digits in hundreds or thousands of dimensions. This is the document matrix again, the same one that I presented before. And one of the things that I've been working on in the past several years, as well as many other people in the machine learning community, in statistics, and in applied mathematics, is how do you try to represent this data in a useful way, or how do you try to find good parameters for these data sets? And if you think of this geometrically, it's a point cloud of about 1,000 documents in 1,000 dimensions. But you can represent it down in low dimensions by constructing nonlinear maps, and it's not so crucial how I did this right now, but you can get pictures like this, where every point is a document projected down from very high dimensions to low dimensions. And I also color the points by topic. So there are documents of different topics in 9 different fields, and you can see that different colors tend to lie in different regions of space, very, very, very roughly speaking, and which bodes well if you try to do some sort of clustering or things like that. And here is a different projection where you turn things around and you navigate a low-dimensional representation of that data. You also see that there are sort of low-dimensional structures, and you can ask lots of questions about this type of data. Can you capture any sort of geometric properties? Can you estimate what the intrinsic dimensionality of this data is? That's often much, much lower dimensional than the ambient dimension. Can you sort of parameterize, in some sense, these data sets? And can you use all of this to do some sort of machine learning task? So what does this have to do with graphs? Well, the way we try to answer several of these questions actually is by mapping these data sets to graphs. And the way we do that is the following. It's very It's a very basic construction. So you think of these points as being in high dimensions, and then you assume that somebody hands you a similarity function, which is a function of pairs of data points, which returns a non-negative number, which you think of as similarity between that pair of points. This is application specific. The way we think of it, or a typical example of that, is a Gaussian decaying function. That function is essentially assigning very high similarity to points which are closer than a certain scale, square root of sigma, and assigns zero similarity to points which are farther away than that scale, like points which are farther away than 5 square root of sigma are just far away. The similarity is 0. But in general, that W is application specific. If you talk to people that study documents, they have an idea of which similarity you should be using for documents. If you talk to people looking at images, they have a completely different similarity function and so on. So we assume that it's given to us. Given that, we can construct a weighted graph from the data set where the vertices are the data points and are connected by edges weighted by that similarity. And whenever you have a weighted graph, you have lots of sort of canonical objects on that graph. Perhaps the most canonical one is the random walk. That's supposed to be a Markov chain on the data set. And in order to define that, you need to give the probability, assign probability of jumping from data point I to data point j. And well, we would like to pick that equal to our similarity function. The more similar j is to I, the more likely I should be to jump from I to j. Well, we can't quite do that because otherwise the probabilities don't sum up to 1. So we simply normalize our weight matrix. The Wij is the similarity between I and j. We divide by the row sums of W, and we get a stochastic matrix P, which represents this random walk on the points. And so these are this process is completely intrinsic on the data. It lives, if the data is on a manifold, lives on the manifold, or otherwise it's just a random walk on this weighted graph. And there are some people talk directly about the random walk. Some other people like to symmetrize the random walk. You see that even if W is symmetric, then when you construct PP is not symmetric anymore, and we're going to do some spectral theory, and one might be worried about the lack of symmetry, but this is conjugate to a symmetric operator. That's completely equivalent to asking that the random walk is reversible, and so there is no problem doing any spectral theory. The eigenvalues of T are the same as those of P, and the eigenvectors are essentially the same. Some other people talk about normalized Laplacians. That's just 1 minus T. So anything that we can say about this operator, we can transfer to this and that and so on. And some other people like to think in terms of the Higgs kernel, but they're all related. So what can we do with this random walk? It turns out that we can do many, many things. Let me just mention briefly how I obtained the pictures before I move to a sort of multiscale analysis. So the random walk has some properties which are essentially immediate from the definition. Pxy is the probability of jumping from x to y. If you raise that to a t, it's just the probability of going from x to y in t steps. I also like to think of ptx, comma, dot, that would be one row of that matrix, as a probability bump on the graph. I like that because, you see, in Euclidean space, we know how to construct bumps. For example, we have Gaussians, we have splines, we have localized functions. How do we do that on graphs? Well, we can look at the rows of the matrix P. In fact, the rows of the matrix P to the T, and T suddenly is giving us bumps at different scales. These are like quote-unquote Gaussians on that graph. As I already said, P and T are similar, so we can look at either one of them. Computationally, think of P as a very large matrix. You have n data points, P is n by n, but we think of it as being very sparse in the sense that we usually like to think that every point has only a small number of points which are really very similar to it. And so most of the similarity are 0. We might threshold them out, and we only retain order 1 entries, non-zero entries for every row of P. And there are theorems that say that if points are sampled from a nice manifold, then all of these operators converge to operators which are canonical for the manifold, like the Laplacian, the Higgs kernel on the manifold, and so on. So we can use these bumps actually to measure distances between points. I'm going to work with T, but I might as well be working with P or any of the other operators. And how can we measure distances between 2 points? Well, instead of doing shortest path, which is kind of unstable, as soon as the graph is perturbed a little bit, I'm going to do something slightly different. I'm going to put a delta function at x, and I'm going to diffuse that for t steps. I'm going to put a delta function at y. There is no microphone right here, so it shouldn't be this. Okay. So I put a delta function at y and diffuse for t steps. I get two bumps on the graph, and I can compare them as functions on the graph. If they overlap a lot, there were many ways of going from x to y in time t. If they don't overlap, there were no paths going from x to y in time t. And you can write that down as the distance between the two bumps. And you just expand everything in eigenfunctions, and you get that you can approximate the distance by a quantity like this. This is an m-dimensional vector. M is a parameter, where the coordinates are simply rescaled values of eigenvectors evaluated at x. And this is also an m-dimensional vector, which is made of looking at the eigenvectors of t evaluated at the point y. And this distance is a Euclidean distance. So what do we find? That if we want to compute these distances between points on the graph defined by diffusion, we can simply approximate that by a distance in Rm for this sort of feature vectors. So immediately you are handed a natural map from the graph, an arbitrary graph. It didn't have to be Euclidean or anything. It's an arbitrary graph to Rm that sort of tries to preserve the distances, these sort of diffusion distances on the graph, and maps them to Euclidean spaces. So this is a map that takes every point on the graph and gives you an Euclidean picture that sort of preserves those distances. And why this has been used a lot by several people. And why is this useful? It's useful because it does some magic tricks when you want to discover clusters, and a little bit appeared in a talk yesterday. So this is spectral clustering in one slide. So suppose you have a point cloud like that, and you connect every point to the nearest 5 or 10 points. So you get a graph, and you would like to say that in that graph there are two pieces. Well, if you just use the map that I described before, so you construct the operator t, or the Laplacian, and you find the eigenvectors, and you map every point to the value of the first two eigenvectors evaluated at that point, you get this picture. So the core of the graph ends up over here, the circle around that core ends up over there, and then it's trivial to see that there are two clusters. And all of this was completely independent of the shape of these two clusters. All that mattered was the fact that there was a sort of connected region of the graph which was weakly connected to another strongly connected region. It doesn't matter what the shape is. And when we work in high dimensions, we have no idea how these shapes are. And so these sort of techniques are largely independent of that, of those shapes. And as you can tell, there is also noise and so on. So there is some connectivity between the two clusters, but it's weak, and the method handles that pretty well. OK, so it has some flexibility and robustness. So these are sort of global things. I mean, if I had different clusters inside the big clusters, I wouldn't have been able to detect them by using eigenfunctions. So how can you sort of do things hierarchically? And this theme also appeared yesterday in Mark Newman's talk. So we would like to do two things at once. One would be sort of build hierarchical clusters on the graph. But you see, most of the times, at least in machine learning, we're interested in making predictions about the graph. We have a function on the graph, like this document is a document about mathematics, this document is about physics, and so on. Or this is a picture of digits 0 or 1 or 2 or 3 or 9. So we have functions on these graphs. And we're interested also in producing dictionary of functions on the graph and use them in order to make predictions. So we would like to do both of these things, hierarchical clustering, if you want, and building multiscale functions on the graph. So the way we do this, and this is joint work by Rafi Kaufman, and this dates actually at least 2 or 3 years back, but it's sort of the building block for what I'm doing next, is the following. So we observe that the matrix T is large and sparse, but if you start taking powers, it becomes low rank. And why does that happen? Well, think about when you take rows of T, of the powers of T, these are bumps on the graph, like Gaussians on the graph, that are getting wider and wider. And so, if you start from 2 nearby vertices, these Gaussians are very quickly becoming almost linearly dependent, which means that the rank of the matrix should be dropping. And here I'm plotting a typical spectrum of the matrix T, which has some decay. As soon as you start taking powers of T, the spectra decay more and more, simply because the spectrum of T is always bound between 0 and 1. And so this is a spectrum of T. Then this is a spectrum of T cubed, T to the 7, T to the 16. I'm just taking dyadic powers of the operator T. And so the idea is that, well, if you look at the spectrum of T, you should be able to truncate. Think of these axes as parameterizing eigenvalues or eigenvectors. Then you can throw away eigenvectors which have frequency higher than a certain amount, that's on the right of this eigenvalue. And if you take an even higher power of T, you should be able to throw out more. And if you take an even higher power, you should be able to throw out more. Now, here, you can think of having the eigenvector sitting in here, but I don't like eigenvectors because these functions are global. They don't capture local information. So we would like to have a way of constructing localized basis functions in each of these smaller and smaller subspaces. And this is for those of you that do signal processing, it's sort of like going from Fourier analysis to wavelet analysis. And this axis, you should think of as being the Fourier axis, literally. So pictorially, what we're trying to do is the following. We're going to start from a point. So here I picked a two-dimensional point cloud so that I could represent it very easily. I connect every point to its 4 nearest neighbors. And I'm going to diffuse 1 time, 2 times, 4 times, 8 times, 16 times, and so on. And what I represent up there is what happens when you diffuse from one point, just 2 steps, say 8 steps and 64 steps. You get this sort of Gaussian bump on the graph. And what the algorithm is going to do is the following. It's going to look at not just one such function, but all functions that are obtained by taking one point and diffusing 4, 8, and 64 times. And it's going to ask, well, do I need all of these functions, or I can throw some of them away because they're almost linearly dependent? And so what it does is at every scale, it diffuses a certain amount. It looks at all the bumps on the graph after that diffusion time, and it's going to pick a well-selected subset, which is the minimal necessary to span all the other bumps that get thrown away. And the way I represented it, and I can barely see it from here, so it must be harder for you, but I put red dots on the points that get selected by the algorithm. And so there are lots of red dots up there. Lots of the small bumps are necessary. But as we diffuse more and more and we have wider and wider bumps, less and less of such bumps are really necessary to span the space because the space is shrinking. And so the number of red dots diminishes. And so you can think of this as downsampling the graph. But the algorithm does more than that. It also tries to compute accurate connectivity between the vertices of the downsample graph. This also came up yesterday in some of the talks. In those circumstances, the calculation of these weights was trivial, but in general, it is not trivial. I mean, you downsample a graph, you have good representatives, but then what is the diffusion rates between these vertices that are left? And so the algorithm produces edges and weights these edges carefully in such a way that the diffusion of this coarse graph should resemble, in a certain sense, the power of a diffusion of the original graph. And let me tell you how it does that. So essentially, we'll produce these subsets of the vertices. It will produce edges, and it produces a matrix, which is becoming smaller and smaller. Originally, it's a diffusivity matrix on the whole graph, but then it's becoming diffusivity matrix on downsample graphs. And it has a guarantee that these compressed diffusions are accurate in some sense. And you can think of each of these coefficients on each of these edges as summarizing the conductivity over many, many edges connecting the two downsampled vertices in the graph. Okay. So how does the scheme work? Very, very quickly. So we start the top row. We start at the top left. Phi0 is just putting 1 unit of it at every vertex. And then we diffuse. We go down along the vertical row. We apply T. T is 1 step of diffusion. We get lots of bumps. And we ask how many such bumps really span the whole space. And we downsample. So the diagonal error is a downsampling operation that selects a good subset of the bumps that span up to a certain precision the space spanned by all the bumps at that scale. And the selection procedure produces phi1, which is a well-selected set of bumps. We call those scaling functions as scale 1. And then we simply repeat. We're going to diffuse these new bumps 2 steps. We're going to get even wider bumps, and we're going to select a good subset, downsample, and we'll keep going like this. And in this way, we obtain sort of multiple scales on that graph. And while we do that, we also compute these powers of the matrix T, T squared and T to the 2 to the j, represented of these new sets of bumps. And these are the compressed diffusion operators at all scales. The details are not terribly important, and I will skip the matrix factorization that does all of this. But let me tell you that, so the construction actually has some guarantee. There are many, many ways of doing hierarchical clustering, compressing diffusion matrices, and so on. The question is is the compressed graph that you give me really representative of the original graph that you started from? And the point is that it's kind of hard to define what you really mean by this. And we have one definition, and we can promise you that the algorithm, when you run it, you specify a certain precision, and the following is going to be true. You can start with any function f on the graph, and you can apply the original diffusion 2 to the j plus 1 times. So the function is going to diffuse out 2 to the j plus 1 times. It's going to become sort of smooth. There is another way of computing it by using the compressed representation. You can take your original function. You can project it down with a projection that is an output of the algorithm to a core scale, to the core scale, to the jth core scale. That's a sort of time scale 2 to the j. You can apply the compressed random walk, just one step of the random walk of the compressed graph. That's tj, just one step, and then interpolate back. That's p vj star. Then we can guarantee that doing 2 to the j plus 1 steps on the original graph is the same thing as projecting down, doing one step, and projecting back up. So for us, this is our definition of saying that the compressed graph is faithful. This is a faithful representation of a random walk at scale 2 to the j plus 1 on the original graph. OK, so in this way, we get a multiscale analysis of the graph. We get some subsample versions of the graph. We get different representations of a random walk at different scales. And we also get a dictionary of functions. These bumps that we produce are a dictionary of multiscale functions on the graph. So we can use them for prediction, for example. This is how that dictionary of functions looks on the documents. I represent the documents down in R3. And every function that we produce is a function of those documents. And so they look like I represent such a function by its value on the set of documents. And these are the functions at scale 3 and different indices. You see, they're sort of localized in different pieces of a document space. And they're localized at a certain scale. And if you go and look at which documents are in the support of, say, F35, you see that these documents are related to each other, as you would expect if this kind of picture made any sense. And then you can look at larger scales, and these functions become wider and wider at different speeds at different locations, depending on the geometry of the graph. And here we go at even larger scale. Now, let me skip this. Can we use this to do any sort of predictions? Well, it's kind of interesting, because now we have built, in this sort of maybe complicated way, but it's really not that complicated once you look at it. We built a dictionary of functions on the graph. Well, let's pick a problem where we want to predict something, so some functions f on the graph. Well, now we can use this multiscale dictionary to do regression on the graph. And it's very natural, as already appeared in the previous talk, that the dictionary is large. And we might want to regularize, for example, by imposing a sparsity constraint. But we are going to impose this sparsity constraint in our multiscale basis. Let me motivate why this might be a very good idea. So let's take gene microarrays, for example. So you have a very large number of genes, say 10,000 genes, a very small number of patients, and you want to predict sick or not sick, for example, or an illness. Just give them the gene responses. Well, if you impose a sparsity constraint, it means that you're looking for 10 genes that allow you to predict. But many genes are very highly correlated in very, very complicated fashion, as we saw in the previous talk. So you might not want 10 genes. You might want, maybe that first gene that you picked is very highly correlated with 30 other genes. So maybe you should put those 30 genes all together in a bag and say, I want to use, the average activity of that genes or a linear combination of activity of those genes as one single predictor. So what I'm saying is that you don't necessarily want to do sparsity in terms of the original genes, but you might want to do sparsity with respect to bags of genes or bags of words and so on and so forth. And this notion of sparsity is completely different, of course. And this is a very well understood phenomenon. The sparsity really is very basis dependent. You can do it in the basis of a gene, or you can do it in a multiscale basis of genes. And so we tried this out. We have a function on the graph. Phi is our multiscale dictionary. And we have a fitting term, as usual, and a two-fitting term. And the sparsity that comes on the coefficients beta jk of the function onto our multiscale basis functions. And the idea is that by imposing this sparsity, we're going to pick up which, if you want, multiscale cluster of genes or of words are most important in order to make predictions. But we only pay the price 1, or rather lambda, whenever we use one such cluster, even if the cluster contains 100 genes. And so we apply this to text documents, the same data set that I described before. And this is sort of lassoing this multiscale basis on the graph. And the results are better than using just single words or doing global SVDs or global eigenfunctions. That's what I mean by Laplacian. And we did the same thing for genes. And we use a standard data set by Nakagawa and others, on which many algorithms have been tried. That's why we picked this data set. It's about prostate cancer and recurrence of prostate cancer. And besides getting algorithms which are getting results which are better than existing algorithms, we also show that really different scales enter in different ways as a way of predicting outcomes. So sometimes, at least the algorithm seems to be showing that some single genes are important, but then some groups of genes really enter as a whole in making the prediction. And this sort of having multiscale folders of genes really helps. So I wanted to now so in this way, we can sort of do multiscale analysis on a given graph. And the question is, can we do something in order to analyze graphs that change in time? And here, to simplify the presentation, I decided to do this by not using the multiscale analysis that I just discussed, by using a very simplified version thereof. So if you didn't like the previous part, I think this part can still make sense. And this is work in progress, actually. So we have a graph that is going to change in time. And it's going to change in possibly weird ways. The weights of the edges might change. New vertices will come up. Some vertices will die. And we want to have some sort of robust tool in order to analyze this. So we have such tools when we analyze one-dimensional time series. We know how to smooth, we know how to regularize, we know how to analyze these changes at multiple scales. We saw some of that yesterday. What about doing something like that for graphs that change in time? So it's a time series of graphs. So what are some of the items on our wish list? Well, certainly we want our algorithm to detect changes, both at large scale and at small scales, provided that it's not just noise. And we also would like to be able to tell us, which location of the graph is most responsible for these changes. We would like to capture topological changes in the graph, but also quantitative geometric changes. Topology is something that doesn't feel the size of the objects. Sometimes that's the thing that we care about, but some other times we want to quantitate the changes because we're going to have noise. We will want to do analysis and statistics. So we want to have numbers that tell us, oh, this part of a graph at this location and scale changed by a certain amount, so that we can do statistics on those numbers. And certainly we want these algorithms to be robust to noisy perturbation of these graphs. If you look at this time series, I think they're going to be really, really very, very noisy. So we propose a multiscale framework that hopefully will have all the properties above. And the idea is very, very simple. So we look at the graph at time t. We do a multiscale analysis of that graph, either as I described before, or just to be independent of what I said before. You can think that you take that graph and you build a multiscale partition. You say you cut it into pieces, then in 4 pieces, 8 pieces, or in some other fancier hierarchical clustering way. For example, as discussed yesterday for multiscale communities. So you get these partitions, and you get one such set of partitions from one time step to the next. We're going to assume that the graphs don't change too much, and that we have IDs for the nodes, which means that we're able to sort of match a good chunk of graph at time t with a good chunk of graph at t plus 1. So we can match also the partitions that we constructed. And then we are going to try to check how much the graph in each of the pieces of a partition at multiple scales has changed from time t and time t plus 1. And that's the part that I think it's rather unclear how one should do that, but I'll tell you how we try to do that. So this is all preliminary. We've worked on toy models for graphs. We didn't like very much the models that we found in the literature for sort of multiscale graphs. We thought they were too regular, so we cooked up our toy models. Our toy models are done in the following way. We pick a dictionary of graphs, trees, complete graphs, mesh graphs, and so on. I call them flavors. And then the construction of these graphs goes in the following way. At the coarser scale, you pick one flavor of these graphs, and you construct it. Here, I picked a silly tree with just one level deep, so everything will fit. And then at scale 2, I replace every node in the tree by the next flavor. I think here I picked a complete graph with 5 vertices. And then at scale 3, I'm going to pick another flavor. Here I can't tell what I picked, but I think I picked another complete graph. And why are there different scales? Well, at scale number 1, I pick the weights on my graph to be equal to 1. At scale number 2, I'm going to pick the weights on my graph to be 2, and so on. Think of these weights, if this were to represent any network, think of these weights as being 1 over capacity. At very large scale, you have huge capacity, and finer scales, the capacity decreases, and that's what creates the multiple scales. And in a mathematician's mind, this might even be a reasonable model for some networks. Of course, you could do more complicated constructions where the flavor changes in different locations and so on, and that's not a problem. So just to show you that these graphs do have multiple scales, here I picked one in which at the coarser scale we have a ring, and then at the finer scale we have a tree, and at an even finer scale we have a complete graph of order 3, a little triangle. And if you go and look at the spectrum of this graph, it has several steps. And there are still, in fact, open problems about how to characterize this spectrum, but that's another talk. So there are different steps which sort of denote different time scales, because if you take powers of the random walk, different parts of the spectrum will die at different times, denoting the fact that you should be able to compress this graph at multiple time scales. And in fact, if you run the algorithm that I described before, the sort of multiscale analysis that I described before, up to a small variation, or rather a small variation thereof, you'll be able to pick up all these scales. And actually, you will see that the construction really compresses out the little complete graphs over there, then it compresses out the trees, and then it finds the circle, and then in the end, it compresses the circle as well at different time scales. OK, so in this sort of toy models, what's going to happen in time? Well, we made up some things that can happen in time. For example, if that's the original graph, sometimes a new vertex might come up. And this should be a small perturbation because the vertex comes up into a little cluster. So we would like to say that that's a small change. A vertex might disappear. That vertex disappears. But still, there are 3 clusters. So that's also kind of a small change. Here, an edge became much stronger. Well, if it becomes really, really very strong, then these 2 clusters are merging. So that would be a pretty big change because we had 3 clusters at the core scale, and now we have only 2. Sometimes a new community comes up, and it ties with other communities. That's also a pretty big change because, at core scale, there are now 4 communities rather than 3. And this is another change where many vertices in 2 different communities connect to each other. And so these communities are also merging, and that's a change at a large scale. So essentially, the changes that we have are adding or erasing vertices, adding or removing edges, changing the edge weights, creating new communities, and things like that. So let me just mention a little bit how we can construct multiscale partitions. And I can rely on the fact that already yesterday there was an excellent talk about clustering. So we use the NCAT measure, which was mentioned also yesterday. So what is the NCAT measure? So C1 and CK is a partition of the graph. These are disjoint subsets that cover. Yes? Oh, so this is a mic. Oh, I see. Thank you. I thought this was just, OK, for recording. So if we have K subsets, C1, CK, that cover the graph, and there's disjoint, you define an NCAT measure. That's simply given by summing the similarities for one subset to the other subsets, and then you normalize by the size of the subset. Exactly, the motivation is exactly what was described yesterday, but if you don't do that, you're just going to cut out little leaves sticking out of your graph, while if you put in the volume of a subset, you don't want the volume of a subset to be too small, otherwise that quantity becomes large. When that quantity is small, it means that the subsets are at very few edges going from one to each other, and each of the subset has a reasonable size. That's sort of one definition for clusters. And well, it's very hard to try to minimize this measure of all possible choices of subsets. It's NP hard. There are approximation algorithms. Some people use spectral techniques in order to approximate that. We just heard yesterday about a new technique which might be faster than spectral techniques. So use any of that and use it to partition your graph. And then you're going to partition it at multiple scales. So you partition it once, and then every piece of the partition get partitioned further on, and so forth. OK. Now, how are we going to measure how much a piece of a graph changes from time t to times t plus 1? I mean, I would like to extract a number for how big that changes. The way we do that is by using random walk projected onto these multiscale partitions. So I define the random walk. So the sub-indexing, unfortunately, is a little bit messy. So P sub t denotes I'm going to look at the random walk on the graph at time t. That's why I put t at the bottom and not at the top. And then this is going to be a matrix, which so I'm going to compress it in multiple scales. So I'm going to compress it on the multiscale partition at scales j. That's what CJT is going to be. And this is a matrix that gives you the probability of jumping from one cluster at that scale to another cluster at that scale. So it's going to be parameterized by sets I and L of the partition at scale j for the graph at time t. So Cijt is the ith piece of a partition at scale j on the graph at time t. And the way we compute that is simply by literally taking that piece of a partition, random walking from it, and checking how many random walkers end up in the other piece of the partition. That's what that formula is doing. This is much less fine of what we did in the construction that I described previously. There are no guarantees that these compressed random walks, in fact, approximate in any reasonable sense any power of the original random walk of the original graph. But we try to stay simple. And now we can ask, how much does this random walk change when you go from time t to time t plus 1? And why are we using random walks? We're really using random walks because they're a very stable object. They're measuring all possible ways of going in a certain number of steps from one partition to another. Now, if this number of random walks changes a lot from the graph at time t to the graph at time t plus 1, well, it means that something pretty drastic has occurred. Lots of edges have been severed, or the weights of many edges has been changed, and so on. And so we measure the change between those random walks at time t and time t plus 1 corresponding to the same scale. For example, in Frobenius norm, or you can do finer measurements of that. And in fact, we could do these things in a better way, but this is sort of the simplest version of this story. And let me get to some simple examples. So we take one of these toy models, and we start dynamics by randomly adding, removing edges, vertices, and so on and so forth. And in fact, the probability of adding vertices is larger than that of killing them. So the network actually grows in time. And this is the original network. This is time equal to 1. A vertex appeared over there with some weights to the clusters. And at time 51, where we stop, we have many more connections and many more nodes. And then what I'm plotting here is the change of the random walk at different scales. This is the fine scale. So these, think of being at the bottom of the partitions, and you have little pieces of your graph, and you're asking how much the random walk between these little pieces changes in time. And you will get a graph like this. And if you ask the same question at a very coarse scale, when you have, say, 2 or 3 pieces of a network, and you ask how much the random walk between these pieces changes, you get a different graph. And what you see is that, well, there are situations where there are big changes at both scales, but there are also places where the changes are big at the fine scale and small at the coarse scale. So here I picked one. Here the change at the fine scale is large, but the change at the coarse scale is small. What's going on? You go and look, and what you see is that this was the network at time t. This was the network at time t plus 1. And what happened is that a new vertex was created over there with links only with 2 clusters at that scale. So that's a big change at this scale, but it doesn't affect the larger scale structure of the network. And that's why we have a large coefficient at the fine scale and a small coefficient at the coarse scale. And we just see that from the plots. Here we have a change which is large at the fine scale and large at the coarse scale. What happened? Well, that was the network at time t. This was the network at time t plus 1, where t is that where the peak is. And the new vertex came here, and he has pretty strong edges with both these communities, which were very far away. That's a big change in the network at the core scale, not only at the fine scales, because it's really changed. Here we had a sort of tree structure. Now maybe we have only 2 clusters because so many points came over there. But now this is really changing the topology of the network. We even simulated attacks, and here it's where I'm going to embarrass myself by talking about things that I do not understand. So all the names that resemble technical names like DDoS or wormhole attack are mathematical definitions. They probably have nothing to do with what they really are. So what we did here, we picked the political blog dataset, which was also discussed yesterday. And it has about 1,400 nodes and 19,000 edges. It has more than one connected component, so we look at the largest connected component, which is about 1,200 nodes. And well, we simulate a DDoS attack in the following way. We pick a random node. We pick a set of 100 random destination nodes, and we draw an edge with a weight equal to the weight of any other edge in the graph from that one random node to all of those 100 nodes. And I would like to hear critiques after the talk about why this is unrealistic. And this happens at time 4. And what we're looking at here are the change in the coefficients at the fine scale, coarser scale, very coarser scale. And we see, of course, a big change and at all scales because it's a big attack. Then the attack stops, and then there is a second attack called a wormhole attack, where the 2 farthest points in the graph are connected by an edge. That's a sort of topological change in the graph. And what we see is, again, that another big change happens at the fine scale, but that change is much smaller than the DDoS attack, which was really big because 100 vertices were attacked. And so this is all very much work in progress. I would very much appreciate comments and especially directions on where I can get data sets where I have graphs changing in time rather than playing with toy models that we understand well because we created both the algorithm and the toy examples. And there are many, many open questions. How sensitive these things are. Can we really detect useful things in real dynamic graphs? And which kind of things can we detect in this way? Thank you very much, and I appreciate your comments and questions.
Questions? Well, maybe, since we're already cutting into the break time a little bit, we can take our coffee break and get back here sharply at 11 for our next talk.